Create optical lighting and illumination and laser systems with OpticStudio, the industry-leading optical design software from Zemax.
Good morning, everyone. Welcome to our webinar, Who's Afraid of Freeform Optics? This is a joint webinar between Zemax and SSI, Spectrum Scientific Incorporated. And let's learn a few things about freeform surfaces today. Here's an outline of what we'll talk about. We're just going to show you who the presenters are. SSI will tell you what they're about, some of the challenges of using freeforms, how to use them, the replication process, and then I'll talk a little bit about freeform design and testing in the OpticStudio, and then I'll hand it back to SSI. They'll talk a little bit about manufacturability and metrology and assembly considerations. I'm Erin Elliott. I'm an optical research and prototyping engineer at Zemax, and we have three people who you'll be hearing from Spectrum Scientific. Daphne?
Hello, everyone, and thank you for joining in. My name is Daphne Chakran. I am CEO and president of Spectrum Scientific. My degree is in optical engineering. However, I've been in management, marketing, and sales engineering most of my career. I would like to introduce David Cook, general manager at SSI. He was the engineering manager at PerkinElmer West Coast Optics division, in charge of diffractive and aspheric optics manufacturing. He has a degree in optical engineering. Also from SSI is Dave Erickson, our chief technology officer. He brings more than 30 years of experience in design, manufacture, and production of precision optical components and optical systems. He has worked on some amazing projects. We are honored to have them on our team. Spectrum Scientific has been in business since 2004. Prior to that, we came out of a PerkinElmer division manufacturing gratings and off-axis aspheric optics, and they were in business for 33 years prior to 2004. PE was actually the first ones to patent the replication process back in 1947. SSI's nanoimprint replication process is very stable and established. We are space qualified. In fact, we are currently working with NASA on the ALMS project. SSI has been manufacturing high volume, flat, aspheric, freeform, and reflective optics and diffraction gratings for the UV, visible, and IR regions since 2004. We primarily use optical replication process in our manufacturing, allowing us to supply high fidelity, high specification precision optics at a fraction of the traditional cost. One of our key capabilities is the volume manufacturing of freeform optics, off-axis parabolas, and ellipsoid mirrors, with surface figures down to λ/10 or better. But we also manufacture plane, concave, and convex holographic gratings. These are to be supplied as glazed gratings using our proprietary glazing technique, which not only offers high efficiency in the UV, but lower stray light than conventional ion-etched gratings. Our mirrors and gratings are used extensively in a number of applications, including analytical instrumentation, telecom devices, metrology, and spaceborne instrumentation, just to mention a few. We also offer a range of hollow retroreflectors with return beam accuracies below 2 arc seconds. These retroreflectors are of a rugged, one-piece construction made from solid aluminum, making them insensitive to vibration, position, and movement, and ideal for use in microsyn type interferometers, FTIR spectrometers, and laser-based tracking systems. As well as components, we also design and manufacture miniature spectrometers based around our holographic gratings. Some of the challenges of using freeform optics. The biggest challenge we've seen is opening the designer's minds up to the possibilities and visualization of how freeform optics can be used in their system, how to design and specify so it's manufacturable. David Cook will go more in depth in his presentation. Cost is very important. SSI's process is a lot less costly than you would think. Typical costs for SSI freeforms broken down into two categories. The initial prototype stage, the NREs can range anywhere from a few thousand and upwards, depending on the specification and the complexity. Then in volume OEM production, pricing are similar to precision mirror volume pricing. Depending on yearly quantity, size, specifications, cost can range from a few dollars in commercial applications to a few $100s. So very reasonable. How will you assemble freeforms in your system to keep costs down? SSI can help in the design phase. For example, we manufacture a lot of pin registered parts for our customers to minimize assembly time. Then the latest measurement techniques. How to use freeform optics, add, replace, and redo. Here are some examples of how freeforms are being used by our customers today. Most of the time, they're just looking at existing systems and figuring out ways to optimize. One example is a simple modification of an existing system by replacing, say, a mirrored surface with a freeform surface to get rid of aberrations. And here's your next generation instrument. Another example is redistribution, taking the weight off from one of your expensive tight tolerance parts. Maybe it's too expensive because of the specifications, or it's difficult to assemble and your yields are not the best. Again, look at the system and replace, add freeform to compensate. This can lower cost of overall system and maybe help in the assembly time. Number 3, next generation build of current instrument. One of our OEM customers was able to get rid of 2 optics from their system and decrease the size of their instrument and improve the performance dramatically by utilizing one freeform. Lower cost, smaller and better performance than any of their competitors. After the initial NRE costs for the freeform mirror, which is better than lambda over 10, the cost of the unit is under $200. And in higher volumes forecasted for the end of 2018, their price drops to below $100. And in high volumes, say commercial products, this price can go down even further. Freeforms for volume production have similar costs to precision mirrors in production runs. And last is creating a complete new design. Keeping freeform in mind, these are customers who have used freeforms and can visualize a new system. However, this is a smaller percentage of our current customers. Most of our customers really are just optimizing current systems or next generation builds. And the changes sometimes are only a few fringes of departure from the original optics. But what a big difference in performance. I would now like to hand you over to David Cook, who will be talking about the nanoimprint replication process in more detail, and in particular about his application in the manufacture of freeform optics.
Good morning, everyone. I'd like to start with a brief overview of the replication process for those who are not already familiar with it. Essentially, we start with a high precision master tool, which has been created with a nicely polished optical surface and is the inverse of the final surface tool to be required. Before replication, the master is carefully measured to ensure that the surface accuracy and radii meet the required final specifications. It's then coated with a release layer in a vacuum chamber and a reflective thin film applied onto the release layer, and then a polymer is applied and the replica substrate is joined to the master. Then these parts are left to cure. Once they are cured, they are separated, and it's through this process that the profile of the master is transferred onto the replica substrate, producing a replicated optic that's virtually indistinguishable in performance from the original master, with excellent reflected wavefront and low surface scatter. It's important to note that the replica substrate doesn't need to be a precision machined, as the replication process smooths out the machining imperfections. This process can be carried out multiple times in the same manner, producing as many replica optics as required. Because the replication process allows multiple replicas to be created from one precision part, this process offers many significant advantages over traditional manufacturing techniques, particularly for high volume production. As you can see from the table, as well as being cost effective, replication also offers part-to-part and batch-to-batch consistency and repeatability, with volume production of high specification aspheric surfaces with typical surface figures up to λ/10, or in some cases even better. The replication process allows you to ramp up production volumes without the need to invest in additional capital equipment. In addition, the replication process doesn't require demanding machining techniques. Only the master has to meet a high specification. The replica substrates do not need to be so highly machined because, as mentioned earlier, the epoxy layer smooths out imperfections, and so the optical quality of the master is faithfully transferred to the replica. Unlike a conventional glass substrate, the optic doesn't need to be mounted or bonded to another piece of hardware. The ability to machine the substrate with additional alignment, mounting, and registration features directly onto the replica substrate is a significant advantage. This reduces the number of parts required, cutting down on assembly time, purchasing, and stock maintenance costs. Another potential advantage is choosing a substrate with a low or high coefficient of thermal expansion. This allows for an athermalized design if that's what you desire. All of these advantages make the replication process ideal for the OEM manufacturing of precision optics. So now that we've done a brief introduction to the replication process and the advantages it offers over classical optical manufacturing, I'd like to talk specifically about freeform optics and the application of the replication process in their manufacture. First of all, what is a freeform optic? There are many definitions out there, but we think of it as essentially a curved optic which doesn't have axial symmetry. And importantly, it allows for compound compensation within a single optic. They're really not new. They've been around for, or at least discussed for quite some time. Freeform of optics were first discussed in the 1950s. However, commercial manufacturing didn't really start until the 1970s. Although a lot of the benefits of freeform optics were well understood, the cost and complexity of manufacturing meant that it wasn't until fairly recently that they've started to enter the mainstream usage with the use of replication process, meaning that today's current state-of-the-art freeform optic offered by companies such as Spectrum Scientific is a high volume, high fidelity, high performance optic that in most cases is diffraction limited. So what are the benefits of freeforms over other optics? Well, first and foremost, the single optical surface allows for compound compensation, meaning that freeform optics allow you to redistribute tolerances within your design and possibly reduce the number of optical elements, giving higher throughput. With fewer optics to align, reducing the optical volume of the system offers obvious advantages. And last but certainly not least, because of the freedom it provides the optical designer, freeform optics offer additional aberration correction never before available. If I can direct your attention to the graphic on this page, it's of the Scuba 2 telescope. This is part of the James Clerk Maxwell telescope in Hawaii, and it incorporates 9 aluminum freeform mirrors. This allows it to examine large areas of the sky 1,000 times faster and with a much larger field of view and better sky to background sensitivity compared to the original Scuba telescope, which used all conventional optics. We just talked about how freeform optics offer substantial volume reduction, and this slide shows the great work done by the Institute of Optics at the University of Rochester, illustrating the sort of reduction in optical volume that can be achieved with a compact freeform design, giving a volume decrease of over 80% compared to the all-spherical design. So this seems to be a good point to stop talking about the actual freeform optics, maybe take a closer look at the design side and how Zemax and OpticStudio can help you achieve great freeform designs.
Let's talk about some of the freeform tools that are available in OpticStudio. In sequential mode, we have quite a wide range of freeform and aspheric surfaces. Standard surfaces, of course, allow a radius of curvature and a conic constant. We have a biconic that separates those in X and Y, toroidal and superconic surfaces. We also have a wide range of A-spheres, even and extended A-spheres, Q-type A-spheres, some Zernike surfaces in both phase and sag, and a biconic Zernike, which again separates the surface shapes in X and Y. Polynomials and extended polynomials, and a Chebyshev polynomial, and a grid phase and sag surface, which take in arrays of data. Here in this OpticStudio file, I've created a 3-mirror system. It's just something I mess around with. It's not a complete design or anything, but I am using extended polynomials here. If I look at the dropdown in the lens data editor, I could choose any of the other surface types that are available. For this extended polynomial, the extra terms are stored out here to the right, and the lens data editor contains a coefficient for each polynomial form in this case. Okay. We also have quite a few analysis tools available in OpticStudio. We have some element drawings, surface and curvature tables, power plots, and also this pretty handy universal plot. So let me just go back to our 3-mirror system and show you some of those. The ISO element drawing you can find under the tolerancing tools here, the ISO element drawing. This is a drawing, the screen is showing a drawing of the 3rd mirror, which is a pretty fast, kind of a fast, large mirror. If you go back to the Analyze tab, we have this surface button. If you pull the drop down, you can see that you have different choices for plotting sags and curvatures, and a sag table, which is the kind of thing that you would want to include in your mechanical drawing. The sag table includes the sag data at any chosen orientation. It also contains some valuable information about the best fit sphere that fits your part. This is a false color surface sag plot. So this is here under surface sag, and it's giving this in 2 dimensions. So I've plotted it in false color. There are other options. And here's a sag cross section for the 3rd mirror in this system. You can see that there's a lot of sag departure in this mirror, 30 millimeters. That's probably a little unrealistic. We also have, under the Analyze tab here, we have this PAL and Freeform dropdown. From that, we can plot various things as a function of pupil coordinate or as a function of field coordinate. On this plot, I've just plotted spherical power versus pupil coordinate. If I look at the settings, I can plot other things too. Powers separately in X and Y, and focal lengths if I'm more comfortable working in focal lengths instead of powers. There's various things that I can plot here. This plot is power versus field. So under PAL and Freeform, I've chosen the field map. And in this case, I'm plotting, again, spherical power as a function of field angle. There's also this handy tool under the Analyze tab, the universal plot. I can plot basically any merit function operand, if you're familiar with our merit function operands, in a 2D plot format. So for example, here, I have plotted the RMS spot size versus field angle. If I look at the settings here, I've got X field and Y field, and the RSRH operand is my providing my Z data. So I end up with a 2-dimensional plot of RMS spot size versus field. And here's another universal 2D plot where I've plotted 3rd order astigmatism versus field. So in this case, I've still got X and Y field angles, but I'm using the ASTI, the 3rd order astigmatism operand, to look at the 3rd order astigmatism. So those are some of our analysis tools for freeforms. We also have optimization and tolerancing tools. Some of the optimization operands that might be useful are full thickness of the part. You can measure the full thickness of the part. This just samples the part in a grid, so you don't need to know where the maximum thickness occurs. For freeforms, it might not be at the edge of the center, as it is for more conventional optics. You can pull in power as a function of field or pupil point. You can access this best fit sphere data using the BFSD, so the sphere that best fits your surface. And you can also pull in surface curvature and critically the surface derivative, so the slope of the surface at any given point, any given X and Y coordinate. All of those things can be used to help make your freeforms actually manufacturable. Okay, so let's talk a little bit about optimizing with freeforms. Let's go back to this 3-mirror system example that I've been playing with. This TMA design would traditionally be done with decentered conics. So this first mirror would usually be something close to an off-axis parabola. You might have a hyperbolic convex secondary and an elliptical tertiary. With freeforms, you don't really need to worry about the decenters, especially with the polynomial surfaces. You can just recreate those off-axis conics as on-axis parts. But that kind of doesn't give you the full power of freeforms, because of course, if you're looking at a TMA design with a freeform, you open up the design space beyond what you can explore just limiting yourself to off-axis conics. So the freeforms can result in completely new design forms that you haven't considered before. That said, designing with freeforms does require some cautious work. The optimization for the freeforms typically has many more parameters, so your parameter space has more dimensions than you are accustomed to as a designer of conventional optics. There are some smart ways to reduce the number of parameters. For example, you would never use polynomial terms that violate the symmetry of the system. For example, this system is symmetric about the YZ plane. And so if I look back at my lens data editor for this design, I've disallowed all of the coefficients that have odd coefficients in X. So for example, this X cubed term is not allowed because we have to have YZ symmetry. And this X to the first power term is not allowed because we need YZ symmetry. There are also some other ways to keep your the number of parameters you're using under control. Typically, one would start with the lowest order terms, the power terms, and then perhaps add astigmatism, add things one at a time as needed. With freeforms, it's really easy to create a system that works perfectly at one field angle and has just terrible performance at higher field angles. So in general, you always design these systems with at least a small amount of field so that you can avoid that situation. I suggest that a designer never turn on all the terms just to see what happens. That gets back to this n-dimensional parameter space. We want to limit the number of parameters to an intelligent number. And in the same vein, as you're designing, you would never keep a term that you've turned on that didn't actually improve the performance. You really want to keep the specification of these freeforms as simple as possible. And that means avoiding adding unnecessary terms. Let's talk a little bit now about optical testing of freeforms, because of course, OpticStudio can also be used to model the optical tests for your freeform parts. This is really important because your optical test is usually what sets the limits on your slope and total sag for your freeform parts. So it's always really important to understand your test method and what your limitations might be because of that. So there's a few different optical tests that you might consider. If your part is nearly spherical, you can use unassisted interferometric testing. If you've got a little more departure from a spherical surface, you might consider adding a null lens, and you can also consider adding a computer-generated hologram. You can model all of those situations in OpticStudio. So let's look at that just briefly. Here I've got a double pass system. I'm assuming that out here is an interferometer that's producing a perfect beam of the correct F number. And this is my part under test. Just just as an example, I'm using a parabola here. In the lens data editor, my test optic is here, and I've got a conic of -1. And you can see that around the test optic, I've repeated everything. So everything that appears before the test optic also appears after the test optic. And I've picked up most of those numbers to make sure that the second pass for this system is exactly the same as the first pass. And I can create an interferogram in OpticStudio under Analyze Wavefront Interferogram. Here I'm interfering the perfect beam from the interferometer with the return beam. And this looks like spherical aberration. You can see that these rings are getting closer together as a function of rho to the fourth, as height r to the fourth for height in the pupil. That's what I would expect from a parabolic surface instead of a spherical surface. So right now, our part under test is about 40 millimeters in diameter. And so this parabola could be tested in an interferometer directly without any assistance. If I open up the aperture a little bit so that I have a 60 millimeter part, now I've got a larger part under test. And if I update the interferogram, what we'll see is that we're going to encounter some problems here. So these rings in the interferometer get much closer together. And what we see is that out here, I'm getting aliasing. It's instantly evident that I've got an aliased pattern here. If your interferometer doesn't contain enough pixels, you can easily get into this situation. This part cannot be tested accurately just using this interferometer test. So we need to help it a little bit. In this case, it's fairly easy to add a null lens. What the null lens will do is it'll sit here and it will alter the wavefront so that when it approaches the part, it's a better match. In this case this relatively simple parabolic case that I've chosen, we can do that perfectly. You can't always do that perfectly. The goal is to make the fringes resolvable. So let me just turn on that null lens by adding a material here. If I turn on the null lens, my setup changes a little bit because I have a negative null lens here now. And let's see, I think technically I should open this up a little bit to increase the size of the part, but let's see what we've got in the interferogram first. So we had an aliased interferogram. Now we've actually got a perfect match. We've got a null fringe here. And if you've done a lot of interferometry, you know that you usually would not look directly at the null fringe. You would look at some tilt fringes. And when you've got a null fringe, these tilt fringes will be nicely parallel to one another in your interferogram. So what we've done here is introduced a null lens that creates a wavefront that better matches the shape of our part so that our interferogram is resolvable in the particular interferometer that we're using in this test. Now, for a null lens test, if you need to test this part to 100th wave, your null lens error budget has to be much better than 100th wave. That means for null lenses, you're limited to fairly simple optics that can be fabricated to very high precision. And the maximum slope that you can tolerate on your test part is set by whether you can design and fabricate a null lens for that test setup. Things are a little bit simpler if you think about using a computer-generated hologram. You can replace this null lens with a CGH. And in OpticStudio, you can model that using our physical optics propagation and ZBF files, beam files. So for the CGH, you can create a nice wavefront that matches your part, and the maximum slope that you can tolerate on your freeform part is then limited by the resolution at which you can write the CGH here. You need 2 pixels of a CGH under any given slope, so that you get Nyquist sampling of your wavefront. So you can also do the CGH modeling in OpticStudio. It takes a little bit of work. I'm hoping to get a knowledge base article out about that soon so you can see how that's done. But basically, you would run POP through the system to determine the phase of the wavefront here. You would then convert that into a CGH in an external math program. And then you would run POP again, stopping each time you get to the CGH to introduce the CGH pattern into the ZBF file that the physical optics propagation uses. So all of those test setups can be modeled in OpticStudio, and that is typically what will set your restrictions on sag and slope for your freeform part. So that's a really critical part of working with freeforms. You have to know your test setup. Okay, we've been talking about doing some follow-up webinars on any one of those subjects, so let us know at the end of this webinar if you're interested in any of those topics, tolerancing, further optical testing, etc. And I will hand things back to SSI now for the remainder of the webinar.
Well, now that we've seen how easy it is to design freeform optics in OpticStudio, I'd like to talk briefly about the manufacturing of freeform optics and the metrology side. There are various methods of manufacturing freeform optics, including direct manufacturing using processes such as diamond turning, magnetorheological finishing, and robotic and CNC type machines. But as mentioned earlier, these have severe cost implications when manufacturing in volume quantities and have challenges in terms of repeatability and volume ramping to meet production demands. There are also manufacturing methods such as injection molding, pressed glass, and nano imprint lithography, but these are really more suited to lower quality optical systems, which makes them of limited use in precision volume manufacturing. Then there's the replication process that Spectrum Scientific uses, which is similar to nano imprint lithography and can be applied to glass or metal, and with both curved or flat shapes, and suited for both high volume and high precision requirements. The images on the right are an example of a freeform optic used in the deep UV. The customer required lower stray light and higher reflectivity below 200 nanometers, and the bottom image shows the improved replica that's currently in volume production. On the metrology side, there are a number of contact and non-contact techniques that can be used. Contact probes have resolution limits, and directly touching the optical surface isn't always ideal. Non-contact methods include optical probes or laser interferometry, which offer higher precision, but they usually require stitching or a phase mask to be used as a null corrector. The type of metrology method chosen will be dependent on the specific application, and certain methods may be more effective than others. So now we've explored the design, manufacturing, and measuring of freeform optics. I'd like to touch on some of the key considerations to ensure that what you design can be manufactured in a cost-effective manner. And the first key consideration is to ensure you communicate clearly with the manufacturer. The generalized surface equation, sometimes referred to as the even aspheric sag expression, is what we usually see. It's usually what customers are presenting to us, and this is a feature provided within OpticStudio. So once we have the surface expression, we generate a sag table independently and confirm with the customer that we're all in agreement before we begin ordering manufacturing hardware. And I think at this point it's really important to note that the freeform optic need only be a few fringes or a few microns of departure from the best fit radius or conic in order to be effective. It doesn't need to be a radical shape that you sometimes see in some of these presentations. Other important considerations are with alignment during assembly. Don't forget that freeforms are a subset of aspherics and therefore usually require that all 6 degrees of freedom are to be constrained. So to accomplish this, the use of mechanical and optical fiducials are routinely used to take care of this. The last slide we have is a list of references used to put our slides together, and there's also a few there that weren't in there, but they're very good references as far as metrology and limitations in freeform optics. So I encourage everyone to take a look through that list and read the ones of interest. So in conclusion, I'd like to answer the question posed by this webinar: who's afraid of freeform optics? And the answer is nobody should be. Freeform optics can now be designed in OpticStudio, and Spectrum Scientific can deliver low-cost freeform optics with aspheric profiles in high volumes to exacting specifications, offering significant benefits and cost savings in modern optical systems. Thank you.
Okay, thanks everyone for your time. We are going to go to the question and answer period of this webinar now. If you look at your GoToMeeting controls, there's a field there that says questions. You can type in your questions and we will respond to them verbally over the microphone. We won't type in answers. And so we'll do that for about the next 20 minutes probably, and then we will wrap up here. So please submit your questions now.
The first question is, isn't finding the best fit sphere non-trivial for a freeform optic since we are non-rotationally symmetric? Yeah, that's right. It is non-trivial. It's useful to find a best fit sphere though, because it ties into your interferometric testing. Your interferometric testing will typically remove the best fit sphere. And so what you see in the interferogram is really the departure from the sphere. In order to set up your interferometric test correctly, you do need to make some assumption about the best fit sphere, and it's the departure from the sphere that you care about. Their second question here is, with off-axis systems, it seems like the first order calculations like NA and focal length become unreliable. Definitely. The focal length and the NA change as a function of position on the pupil with freeforms, and the same is true in field. You do need to plot those as a function of field and pupil position. I've also set up merit functions that measure those things for me in particular points that I care about. For example, I might care about the focal length at the vertex and the focal length at the edge, and maybe one point in between. It can help to get that information out of your merit function too. I guess usually I do that with ray-based calculations. So the focal length is related to the shift of the chief ray. The shift of the chief ray on the image plane. So it's fairly straightforward to use ray data to set that up in your merit function. The third question, since more field points and higher pupil sampling is required, it seems like more rays need to be traced. Are there plans for using GPU optimization? Let's see. So I'm not an expert at this. Tom might have something to say about this, but we have checked into using GPU optimization, and we haven't found that it's a significant advantage for ray tracing, especially in sequential mode. I think that's partly because it's already so fast. But we have poked into that now and then. I think it might be that that's the biggest advantage for that would be in your non-sequential mode. But yeah, let's talk about that a little more offline. Let's see. Grant, I think this one is for you. If you are only interested in 1 to 2 freeform parts, is the replication manufacturing method still appropriate?
That's a good question, and it's actually doesn't make sense if you just need 1 or 2 parts, because to do the replication process, we usually order 1, 2, or 3 masters to begin with. And so for prototyping purposes, in small quantities, just have them directly manufactured. And when you get into the higher quantities in the dozens, it's more cost effective for the replication process.
So for 1 or 2 parts, if you're looking for a few custom parts, it's probably more practical to do like a diamond turning process. Is that right?
For a mirror, sure. there are companies who make transmission optics too, MRF or hand polishing, or
Right.
other, yeah, or some other CNC type machines can do transmission optics as well as reflective.
Okay. Okay, the next question is hammer optimization working for freeforms, or should we use the local optimization? So actually, I think this is not really different than anything else. If you're using local optimization, you do want to be intelligent about guiding it to the minimum that you want it to fall into. So you need to use some smart, make some smart decisions about how to do the local optimization. Now that said, if you've found a very nice, a pretty nice solution, hammer can be a useful thing to do. If you turn on hammer and let it run overnight or something, you'll really ensure that you're at the bottom of that local minimum and that you've really found the best solution in that area. Next question, can we have the slide deck or the references mentioned in the slides? Oh, yeah, I think we can post the slide deck. Let's see. I think we can post the slide deck for this webinar when the webinar is posted. Tom, is that right? Can we do that? Yeah.
This is Dave Cook. I think the webinar is available after the close of this session, right?
Yeah, I think we usually post the recording, but I think we can also put a link to the slide deck.
So
I can follow up with an email. I can just put it on my Google Drive and follow up with an email too, if that's necessary. Okay. Let's see. There's a question here. Can you comment on freeform lens optics as opposed to mirrors?
Well, I think the principles apply for manufacturing and metrology. I'm not sure I got the question right, but I think in the design space as well, don't you think, Aaron?
Yeah, are there more limits on the refractive, refractive system with two surfaces versus replicating one mirror? Is that harder, more difficult, or?
I'd say the folks that do transmission optics have that under control. They use their alignment techniques. Usually it's a pressing or a CNC type manufacturing operation, and they handle that in their way. Here at Spectrum Scientific, we do all reflective optics at the moment. Transmission optics is in development, but that's usually handled through the CNC machines.
Yeah, I guess I can see that because you've got another set of problems that could crop up with the refractives. You have to position that second surface correctly with respect to the first, and et cetera, right?
And probably twice as much metrology effort as well, because you measure each side and the relationship between each side of the lens.
Right, the position of each, the final position of each replicated part with respect to one another. Okay. The next question is for you too, Grant. How many replicants can be made from a master?
The answer is thousands. We are in production right now with a single. We always have a backup master, but we're running the same master for over 10 years already, and we've produced thousands of parts from it. So.
Okay. So the masters don't really wear out or degrade?
Right, and just to make it clear, we'll take a submaster and then make and step down away from the master to preserve the master, and you get many hundreds of takes off each submaster. So.
Okay. The next one for you too. Are there versions of your products that are suitable for high vacuum applications?
Absolutely. We are space qualified. All these optics get coated in 10 to the -6 kind of vacuum pressures. They're low outgassing, low condensable volatiles. We're NASA qualified, so they're very sensitive to the vacuum environment. So, and we do a lot of work in the deep UV, and those folks are sensitive to contaminants as well.
I think one of the reasons NASA is sensitive to contaminants is that the struts that support the Hubble Space Telescope breathe because of outgassing. So you actually have to follow the telescope in its orbit and adjust the focus, which is just because of outgassing problems, which is interesting.
That is interesting to know. Hopefully they've
Yeah.
hopefully overcome that now.
Yeah. Yeah, it did stabilize, but it never went away entirely, which is funny.
So I think we already answered the question.
Yeah, we answered the next one. How many terms are usually used for a freeform optic in OpticStudio? So that depends on the type of freeform that you're using. But for example, the extended polynomial has, I don't even remember what the limit is. Its limit is very high, like up in the thousands or something. That said, you always try to design with the minimum number of terms. There's no reason to put extra terms in your system that don't really improve the performance and just make life harder for the manufacturer. So I think it's fairly rare that you would end up with, hundreds of coefficients on an optic, just because those higher order terms stop affecting your performance, at some point. There's a question here, when will full field displays be available with ZMAX? Let's see, maybe you could elaborate on that question a little bit. We looked at the universal plots and the power as a function of field plots. The universal plots let you plot different aberrations and as almost anything as a function of field angle. So there's a lot of bases covered with those plots. The next question is, does RMS slope properly limit MSF errors, and how do you define that within a design? Actually, I'm not sure what what's MSF? Could someone fill me in there?
Mid-spatial frequency?
Oh. Yeah, okay, so yeah, let's talk about that a little bit. In theory, you could control this. You could control this by measuring the slope on a part with high enough resolution. So, for example, we have an operand that measures the slope. You could set up a measurement of a grid across the part that's high enough to capture any mid-spatial frequencies that you're worried about. I could imagine if you were doing, for example, diamond turning and there was a certain mid-frequency, a specific frequency that you were worried about, you could sample the surface specifically at that frequency. Something I might consider doing in that case is writing a custom merit function operand. So I could use ZMAX's ZPL language to write a little calculation of what I'm trying to measure and return it to the merit function. That could be a pretty powerful tool for controlling a specific spatial frequency that you're concerned with. Oh, and actually, someone helped us. Someone at ZMAX reminded me that we do have for the previous question, we do have full field aberration plots coming in the next release, and we'll have some betas. We'll have some betas available for that soon. If you want to take a look at those and be a beta tester, just email us at support@zmax.com and say that you're interested in beta testing those plots. There's a question here. What are the 6 degree of freedom constraints? Is this I think this is the, Grant, you mentioned that the part has to be aligned in 6 degrees of freedom. Maybe you could elaborate a little bit on how that might be done?
Yeah, that not necessarily how it's done, but what are the question is, what are the 6 degrees of freedom constraints? So it's 3 laterals and 3 angles, XYZ translation, XYZ tilt. Those all have to be constrained during alignment. So mechanical fiducials and optical fiducials are routinely used. So if it's a round optic, you need to control it rotationally. and laterally and X, Y, and Z. That's what we meant by 6 degrees of. So people call it 6 degrees of freedom. Well, there's 6 degrees of constraint with a freeform or any off-axis segment.
Yeah. So you might put mechanical. Maybe you could help me a little bit too. So you might put mechanical marks for use with, say, an alignment telescope, something like scribes on the part in specific locations, for example.
Right.
Or
like
you might maybe.
I'm sorry, that like outside the clear aperture, put some fiducial marks or flats on the, if it's a round part, you might put a flat somewhere on it to reference the back.
Yeah, and the flats, and these might be polished flats that a distance measuring interferometer could use, for example.
Yeah, they could be polished. One of the beauties of the replication process is that you can have mechanical interfaces that aren't directly on the optical surface, but the optical surface is aligned relative to those. So, you know, you can imagine having a right angle post with a plate and some pins and a flat, and have the optical surface orthogonal to that and aligned very precisely. A really simple integration of complex systems.
I see. And because you've got the master to measure, you can locate those very precisely with respect to, say, the vertex of the optical surface.
Correct. Yeah. Okay.
Okay. So there's a question here about, a follow-up to the best fit sphere question. Since only the Y coordinate is provided in OpticStudio, then we can't necessarily directly provide the seg table to the fab house. Okay, so there's, I see what you mean. So the seg table in OpticStudio just gives you one orientation. In the settings, you can change that orientation. So you can create the seg table over different clocking angles. So you might want to provide your manufacturer with these freeform parts, obviously with more than one seg table. You can also get the two-dimensional seg table data, though, from the 2D plots. If you go to the text tab, or it's either the text or the data tab, you'll see that that data is available if you want to just provide a grid to the manufacturer. The next question, are there plans to add Chebyshev optimization to OpticStudio? Zernike's are nice, but many times optics are rectangular. So you can already put Chebyshev surfaces in OpticStudio, and you can optimize on those coefficients. Because you mentioned TESI, I wonder if you're asking about tolerancing. So you can use T-Park command to tolerance on any of the parameters in any of these freeform surfaces. Tolerancing on the coefficients, that would let you tolerance on the coefficients directly. That's not always what you want to do. Sometimes you want to use the tolerance scripting tools to make sure that you know the RMS that you're adding to the surface. You could email us at support for a follow-up on that if your question is really about tolerancing the Chebyshev surfaces. The next question is for Grant. How large can a freeform mirror be for manufacturing? Is 1 meter diameter currently possible? Actually, I guess I have a bit of a comment on that. I know that it's possible to do 1 meter off-axis conics. The telescope world does that fairly routinely, but of course it's hugely expensive. And it takes very specialized equipment. Grant, do you want to comment on how large you guys can do?
Yeah, I mean, theoretically, sure, it can be replicated to 1 meter, but it has to fit in the coating chamber. So it's a pretty big mirror to put in our coating chambers. But we have done stuff up to 11 inches in diameter.
Okay.
But again, that's pretty big. You only get 1 or 2 in the coating chamber, and it drives up the costs. You know, it becomes an expensive optic, but it can be done.
Yeah. Okay, 11 inches is fairly large if you're not in the telescope world anyway.
Yeah, I mean,
okay. Next question. The next question has to do with converting between surface types. We do have an aspheric conversion tool. Okay, so the question, let me read the question first. During the design process, I would like to test some different surface types. Some surface types can be converted exactly, like Q-type to A-sphere. Other surface types can be fitted. Can this fit and conversion routine be added? We do have a conversion tool under the optimization tab. There's a convert A-spheres tool. If you haven't messed around with that, play with it a little bit and see if it has the capabilities that you're looking for. And then, of course, if it doesn't, we do keep feature request lists. So definitely email us at support@zmax.com on exactly what you would like to see that tool do. Okay. The next question is, up to what order can a mirror be manufactured? A prescription of surface sag with terms up to order 10, is that something that can be manufactured?
Yeah, I guess that's a SSI question.
Okay.
Yeah, the order of the terms doesn't limit the manufacturing. I mean, the 10th and 12th orders are pretty minor adjustments when you get out there. If it can be, I've never seen it be a limit. It's a prescription that can be made and manufactured. More importantly is, can it be measured routinely and conveniently? But as far as I know, that you agree, Dave?
Surface slopes
might become an issue if it gets too perturbed.
Right. You may not have enough data in your analysis, in your metrology to do high slope surfaces. But if the surface is non-reentrant, then it can be replicated and manufactured.
So it can be replicated, but measuring it
is difficult.
Yeah. Okay.
Yeah, and you can make an optical model of your test setup to see if the slope is so high, the fringes in your test can't be in your interferometric test can't be resolved, and that's often what limits your max slope on these parts. And
that's what you demonstrated earlier, right?
Yeah, yeah. Briefly, very briefly. Let's see. The next question, how do we perform a tolerance analysis in ZMAX for a reflective system with freeforms? So tolerancing the position of the part is done just as usual. You can insert coordinate breaks to tilt your part. You do want those coordinate breaks to reflect the physical reality of your system. So wherever the pivot point for your freeform is, you do want to set up your coordinate breaks so the part pivots as it does in real life. We have a knowledge-based article called How to, it's called How to Pivot an Object About Any Point in Space. Might be useful if you're working in sequential mode. And then the tolerancing the surface irregularity is a little bit trickier. You can use the TPAR commands to tolerance the coefficients directly. When you do that, you do need to go back into, for example, your Monte Carlo files and check what the RMS deviation was for the part, because then in that case, what you put in is the tolerance that you can allow for each coefficient. So you might need to go back and calculate the RMS irregularity that you introduced during that tolerancing. You can also use scripted tolerancing to control how the coefficients are added to the part. That's a little trickier, but then you can control the RMS that you're introducing during the tolerancing. Okay, let's see. Here's a request to make sure to email a link to the presentation. We'll do that. We'll find a way to make sure you can get the slides. This is another, I think we talked a little bit about this already. What's the best way to specify mid-spatial frequency using OpticStudio? And can we use a freeform surface to simulate the mid-spatial frequency error? Oh, okay, so the second part of that question. So something that I've done when I want to simulate a specific mid-frequency is actually, in the case I was doing, I had rotational symmetry for the rip. It was basically rotationally symmetric ripple. And so I ended up using a Zernike phase surface. I put it in front of the part so that I could add a ripple function to it. So the higher order Zernike terms like rho to the 8th, rho 10th, rho to the 12th start to look like rotationally symmetric ripple. So you can use those. You could use the Zernike surface to put that kind of ripple into your system if you want to. You could also use an off-axis piece of that. If your ripple is not symmetric about the vertex of your part, you could use an off-axis chunk of the Zernike phase surface to put that in. You can put in ripple with an extended polynomial too, which would separate the x and y coordinates and give you a little more flexibility in how to designate how to get that ripple in place. Next question, what do you think about the novel methods for the optical characterization for freeform optics? I guess maybe I would need to know what novel methods you mean. Certainly, different applications care about different aspects of these parts. So I do notice that people working with freeforms create a wide variety of custom analyses, as well as the built-in things that are available in the optical codes. Next question, someone has pointed out that the full field displays show the direction of the aberrations as well. Yeah, that's right. Which of course is especially important for astigmatism and coma too. And so those plots are coming into OpticStudio. The beta testing will be available soon. Email us as support and say that you're interested in beta testing our full field aberration plots. That way you can kind of influence what you would like to see in those plots. Are there plans to add a NURB surface to Zemax as the ultimate freeform describing polynomials? Yeah. We have kicked that idea around. It's on our list. We don't know when, we don't know yet for sure when or if we will implement that, but we have had some discussions about it. So, yeah, we understand that NURB's surface would allow you to optimize the freeform shape directly instead of working with coefficients in a polynomial representation. So we have had people asking for that. Okay, we are almost out of time. Let's see. So the next question, I think we kind of addressed. Sander, if you email us at support, we can talk more about tolerancing the irregularity for these parts. Someone commented they are interested in the follow-up webinars on tolerancing freeforms and optical testing freeforms. Yes, I would like to do those too. I'm very interested in that topic. I think there's a lot of interest among our customers. So we'll see. Hopefully we can get to those. Thank you everyone for joining the webinar. That was a lot of fun, and we hope to see you at some future webinars. Bye everyone.